Welcome to another module of this course, Microwave Integrated Circuits. We are in week 3, module 4. So, in the previous module, we had discussed about the properties of properties of the S parameters for a two-port network, and then we had derived the expression for the input and output reflection coefficients. And then I said that there is a method to make this computation of the reflection coefficients, or for that matter any ratio term that involves, there is a ratio of either the incident wave or reflected wave, not just at one port, but say the incident wave is at one port, the reflected wave is at port 5, port 6, port 4. And if you want to find out the ratio of these two quantities, then there is a simpler method, and that is called the signal flow graph method. So let us see what is the signal flow graph method. So signal flow graphs what is it? It is an analysis technique applicable to S parameters a means to and also it is a means to visualize the power flow these are the two things. So let us go back to our two-port network. First of all, every incident or reflected wave is represented by a node, and a node is represented by a small bubble. We have 4 incident and reflected waves, so we have 4 nodes this way, B2 and A2. Now, we know that A1 and A2 give rise to B1 and B2 as described in our two-port network, isn't it? Because if we write down the equations as applicable to just this two-port network, the equations are SB1 is equal to S11A1 plus S12A2, and B2 is equal to S21A1 plus S22A2. So we can see that if we consider just this network, then it seems it is that B1 and B2 are caused by A1 and A2. So it is like A1 and A2 contribute to B1 and B2. In other words, power is flowing from A1. It is A1, the power flowing in A1, that is giving rise to B1. So when we have one variable or one node contributing to another node, we draw a line or an arrow between the two. So here from these equations, A1 and A2 contribute to B2. Similarly, A1 and A2 contribute to B1, and the magnitude by which of the contribution for each, that is A1 times S11, S11 times A1 is contributed to B1. So that S11 will be the weight of this branch joining the two nodes. Similarly, this will be S21, this will be S22, this will be S12. Fine. Now, as we shall see, this is now from here it might appear as if only A1 can give rise to B1, but that is not the case. It might be that through another process, for example, if we connect there is a generator load present here, then B1 will also contribute to A1 in a recursive manner. So let us see a simple example, a simple two-port network with both its input connected to a generator and an output connected to a load. So the circuit diagram for that, let us say Z0 is the characteristic impedance at both port 1 and port 2 of this network. ES is the source voltage. Now, we can suppose Vg is the voltage that is applied to the two-port network, then we can write an expression for Vg as equal to Es minus I1 times Zs, where I1 is the current flowing into port 1 and I2 is the current flowing. From here we can write this as now this is the circuit equation in terms of voltages and currents. If we now convert this in terms of the normalized voltages and currents, normalized incident and reflected voltages and currents, what we get is, following from the previous equation, and simplifying this, what we will get is now this term, if I represent it by, is actually the source reflection coefficient or generator reflection coefficient, and this term, this whole term, if I represent it by a term Bs, then I can simply write my A1 is equal to Bs plus B1 gamma s. And if I now draw the signal flow graph diagram of this entire circuit, so we can start with the first, just for our two-port network as we had seen. This is the basic signal flow graph diagram. And in addition to this, we also have the equation for our load. So we know that A2 is equal to B2 times gamma L. So then what that means is that we have now B2 contributing to A2 with a multiplicative factor gamma L, And we also have seen that there is another equation A1 equal to Bs plus B1 gamma s. To do that, what I do is I take another node as the wave Bs, and it contributes to A1 with a magnitude 1 because Bs is not multiplied by any term here, and there is this gamma s contributing back. So, B1 is also contributing to A1 with a multiplicative factor gamma s. Now, using this, first thing that we have to see is if we want to find out the value of gamma in the previous module we saw was given by this relationship. Now, the question is, can we use this signal flow graph diagram to simplify our equation to find the same relationship? So, in order to do that, there are some rules for simplification of signal flow graphs. Suppose you have a signal flow graph diagram like this. Then this is equivalent to this. If you have a signal flow graph diagram like this, then it is equivalent to this. So, this is like the distributive property of signal flow graph diagrams. Similarly, if you have a signal flow graph diagram like this, that is two signal flow graphs following each other, and that is equivalent to this. If they are in shunt like this, then that is equivalent to this structure. So, here we have a loop with magnitude T1, T2, and finally, if we have a loop, like this, then that is equivalent. We can remove that loop and have an equivalent circuit like this. So, now let us go back to the original to the signal flow graph diagram for the two-port network that we had discussed a few moments ago, and see whether we can get a similar, we can decompose the signal flow graph diagram and obtain the simplified version of it. So this was the signal flow graph diagram that I had discussed a few minutes ago. This is for our 2-port network with both the load connected to ZL and the source connected to a generator with internal impedance ZS. Now for this, if we let us just see the load, since we are trying to find out gamma in, let us just draw the circuit with the load in it. So the signal flow graph diagram with just the load will be now look at this loop that is there. This is a loop, and what I do is, instead of having a single point A2, let me split this loop. What I mean is, I now have gamma L here, S22 here. I also have gamma L here. So what I did was, I took 2 points, I split this node A2, and I have now multiplied both the A2s with, I have provided a path with magnitude with weight gamma L to both these nodes A2. So then so what I have done this way is that I have now removed this loop and made it a loop, a single loop like this. So then this is from the identity that I just discussed previously, this identity, that this, when a loop like this is present, I can, the equivalent circuit, equivalent signal flow graph diagram will become like this. So I simply apply that this identity, and my signal flow graph now simplifies. So from here I had come to this point, and now I am going to this point. So now only this path remains, gamma L. This loop will be absorbed inside this this path with a weightage of fine. Now, so now I have, now this becomes a simple thing. This is just 2 parallel paths, one path is here and this is here, and so this whole, since I have to go from A1 to B1, this whole thing can be simplified to this, where gamma in is just the addition of the total path product along this path, along this path, and the total product of the weights along this path. So along this path, the total product of weights is what? Gamma L times S21 1 minus gamma L S22 multiplied by S12, and along this path the total weight is this. So then this is, this expression gamma in is equal to this, which is same as the expression that I just derived earlier. Now, I would like to add some more. So this is more or less how signal flow graphs are analyzed. There are of course some specialized rules called Mason's rules uh, that if we probably in some future module we will be covering that. But I would like to now, in addition to the Z and Y parameters that I described in the past few lectures, I also said there are S parameters, as that is what we have been discussing extensively. But another class of circuit parameters called cascade parameters or ABCD parameters are also quite useful while describing microwave circuits. So let us see what is ABCD or cascade parameters. So ABCD and ABCD or cascade parameters relate the input and output voltages and current, input voltages and currents to the output voltages and currents. The advantage of an ABCD parameter is that if you have say two networks connected in cascade like this, and say the ABCD parameter matrix of the first network is M1 and the second network is M2, then the overall ABCD parameter of this cascade will be M1 times M2. That is the biggest advantage. And now in passing I might also refer that where are the Z parameters that we described for a circuit. Okay, we have seen the application of S parameters, but is there a situation where we have two networks and the analysis of those two networks using Z parameters or Y parameters might actually be more convenient as compared to the S parameters themselves. So such a situation actually exists. For example, if two networks are connected in series or in shunt, then actually we just discuss it that the Z and Y parameters might actually be more convenient than the S parameters. Let us see how. Say we have two networks in series. I am calling these two networks to be in series because they have the same currents flowing through them. So this is network 1 and this is network 2. Now for this two combination, the overall Z parameters, Z1 plus 2, is simply the addition of the individual Z parameter matrix. So when two networks are in series, Z parameters might actually be more convenient. Similarly, say if two networks are in shunt like this, then actually the overall Y parameter of these two networks of the combination is simply the addition of the individual Y parameter matrix. Now, so this was the two cases where the Z and Y parameters might actually be more convenient than the S parameters. Now we were discussing the ABCD parameters. Let us see the let us try to find out the ABCD parameters of some common circuit elements that we have been discussing, especially the distributed circuit elements. So what is, say, the, let us, if we consider a simple transmission line. sample ABCD parameters of some common circuit. Say we have a lumped impedance in series, then its ABCD matrix is given like this. If we have, say, a shunt admittance, an admittance connected in shunt like this, then its ABCD matrix is given like this. If we have a transmission line of a certain length, say L, beta L or theta, its ABCD parameters are given by, say, Z0 is the characteristic impedance of this transmission line. Now there are some relations relating the S parameters to the to the ABCD parameters as well, just like the relations we had between the Z parameter and the S parameters. ABCD to S parameters. First of all, if we have a transmission line, then we can define what is known as normalized ABCD parameters. So the normalized ABCD parameters are given like this. So A and D remain the same, C and B are scaled by the characteristic impedances, and all these parameters in the normalized of all the normalized ABCD parameters are dimensionless. Now proceeding this way, we have S11 for a network is given by this. So I will just give one parameter conversion and you can maybe find out for the other parameters. The condition of reciprocity that we saw for reciprocal networks, for S parameter matrix for a in an S parameter matrix for a 2-port reciprocal network, that boils down to this relationship. Now this, it can be shown that in terms of the ABCD parameters, this boils down to this relationship. Here of course note this A bar, B bar, C bar and D bar are the normalized ABCD parameters. Proceeding similarly, proceeding similarly and trying to find out the ABCD parameters, say, of a quarter wave transformer, then we know for a quarter wave transformer theta is equal to 90 degree, and therefore the ABCD matrix will be cos 90 degree, J Z0 sin 90 degree, then J Y0 sin 90 degree, cos 90 degree, and this simply turns out and if we choose to find out the normalized ABCD parameters, then this would come out to with J on the outside. So in summary, I would like to mention that in this module we covered two very important concepts in microwave engineering. One was the signal flow graph diagram, which is extensively used when we want to analyze very complicated circuits with many ports or many circuit elements. and also the ABCD parameters. Though ABCD parameters, they might look like any other circuit parameters like the impedance or the admittance parameters. They are used quite extensively, especially since in microwave circuit analysis, it is often convenient to analyze a circuit in terms of cascaded elements rather than considering the whole element as one. So when we have such a scenario where we have many elements in cascade, we do use the ABCD parameters to analyze such circuits. Thank you.